Okay, last time we said that when we analyze an indeterminate structure, at the end of the day, we will be using relationships between the end forces and end displacements. So our aim here is to define that relationship without being how to solve a differential equation. Okay, this is our aim. So we say that we have a member, and this member can be under any loading. It could be a point load, it could be a uniform distributed load. And this is the local axis of the bending of the member. And let's say that this is point A, that's point B, and this member is having an end forces, end moments as MAB and MBA. Okay, and because of these forces, we will see deformations on this member. So let's define the deformations. That's point A, that's point B. Let's say that point A had a vertical translation, that's equal to YA. Point B, we have another vertical translation, YB. And that's the what we call the chord rotation. And we see a rotation at A, so let's mark it this way. And we have theta A. I'm defining all the rotations in the counterclockwise direction. That's theta B. And that's the deformed shape. So as you see, I define the boundary conditions at both ends of the members as follows. And this is the moment equations. Why did I show only the moments? Because remember that I can represent the moment diagram of this member by using in terms of end moments. Okay, so but let's also show the shear forces AY and BY. But my aim here is to relate the end moments with these boundary conditions or end displacements. Okay, so here I'm saying that I'm looking at this case and I will investigate that in two parts. I'm saying that this is equal to, we have zero deformations at the nodes, okay, and a uniform distributed loading. And in that case, I'll also have some support moments. So I call these support moments as fixed end moment AB and fixed end moment BA. This is the case no deformations, no nodal deformations. In other words, YA is equal to YB, that's equal to theta A, theta B, and that's equal to 0. Plus, we have these forces at the nodes. Nodes are free now. And I will have, let me use the red color again, MAB prime, MBA prime, AY prime, and BY prime. Of course, we have these shear forces here too. And these moments or these end forces will occur due to the end displacements. So we call this only nodal deformations. Which are YA, YB, theta A and theta B. So here I'm doing a superposition. That's my original case. All the nodes can deform and we have a member loading. So I'm investigating this in two parts. In the first part I have the member load but zero deformations at the nodes, plus I don't have any member load. I have some end forces and these end forces are due to the nodal deformation. So here this case is equal to summation of this one plus this one. Okay. Now we will start working on this case. Let's name the cases. So this is our case 1. This is our case 2. Okay, I'm doing a superposition. And at the end of the day, I will have MAB is equal to MAB prime plus fixed end moment AB, and MBA is equal to MBA prime plus fixed end moment BA. My aim here is to figure out what MAB and fixed end moment AB is, and likewise MBA prime and fixed end moment BA is. So I will start working on case 2 now. Okay, so in case 2, let's draw it one more time. I have node A and B. Here MAB prime, here MBA prime, shear forces AY prime, BY prime. Let me draw the deformed shape one more time. Because of these nodal deformations, we will see these MBA prime, MBA, AB prime internal forces. I have a translation, another translation at B. Theta A, theta B, and we expect to see a deformed shape like that. This is theta A, that's theta B. So my aim here is to relate these end moments with these end deformations law, and the problem is simpler than this one because right now I don't have any loading. Okay, so actually if you think about it, this part will always be equal to, will be the same for every member. Okay, it doesn't matter how the members are loaded, this part will is exactly the same for every member. The loading will influence only the values of these fixed end moments, nothing more, but this part always remains the same. That's one of the reasons of doing such a superposition. I separated the effect of the loading plus the effect of nodal deformations. Now let's start. We will do our classical solution. Let's first obtain the moment diagram or the equation for the moment. So I'm taking a section cut. This is my moment. I have a shear force here, AY prime, and I got this end moment, MAB prime, and from that I obtain equation of moment as equal to minus MAB prime plus AY prime times X. Okay, then we can write the differential equation d square y dx square is equal to minus MAB prime divided by EI plus AY prime divided by EI times X. Integrated once, dy over dx is equal to minus MAB prime EI X plus AY prime 2EI X squared plus C1. Okay, So let's put the first boundary condition at x is equal to 0, dy over dx, the rotation at a is equal to theta a. This tells me that c1 is equal to theta a. Okay, integrated one more time, this y is equal to minus mab prime divided by 2ei x squared plus ay prime 6ei x cubed plus theta a times x plus c2. So let's put the second boundary condition at x is equal to 0, y is equal to ya. This tells me that c2 is equal to ya. Now my fourth boundary condition at x is equal to L, y is equal to yb, then yb is equal to minus mab prime divided by 2ei L squared plus ay prime times L cubed divided by 6ei plus theta a times L plus ya. Okay, so let's say that that's my equation 1. Again, at x is equal to L, dy over dx is equal to theta b. Then the rotation at b is equal to ab prime divided by 2ei multiplied by L plus ay prime times L squared divided by 2ei plus theta a. So let's say that that's my second equation. And from that equation, I can obtain ay as equal to 2ei over L squared theta b minus theta a plus 2 mab prime divided by L. So let's say that's again the second equation. Now inserting two into 1, I obtain the following equation. yb is equal to minus mab prime divided by 2ei L squared plus L over 3 theta b minus theta a plus m prime ab L squared divided by 3ei plus theta a times L plus ya. Okay, so dividing both sides, and simplifying, we obtain the following relationship: 3 times yb minus ya divided by L is equal to minus mab prime times L divided by 2EI plus theta B plus 2 theta A. Okay, now let's take a look at this expression, what it means, YB minus YA divided by L. So it is YB minus YA is actually this distance, YB minus YA, and we are dividing it with the length. If you think about it, this is that angle. So if I call this angle as my phi angle, chord rotation, okay, then phi will be equal to YB minus YA divided by L, right? So this is called chord rotation, and according to our derivation, our definition here is measured in counterclockwise direction. Okay, so in order to further simplify that equation, we can write the following: 3 times the chord rotation is equal to minus MAB prime L divided by 2EI plus theta B plus 2 theta A, and remember that the phi angle or the chord rotation is difference between the translations divided by the length of the member. And if I write what MAB prime is equal to, I obtain the following equation. MAB prime is equal to 2EI divided by L. I got 2 theta A plus theta B minus 3 times the chord rotation. So as you see, that's the relationship we were looking for. Not all of it, but some of it. The MAB prime is equal to 2EI over L, 2 theta A plus theta B minus 3 phi. So this is the solution of case 2, right? We already solved this part. We related the MAB prime with the end deformations. If I want to write the actual moment, that will be equal to 2EI over L, 2 theta A plus theta B minus 3 times chord rotation plus fixed end moment AB. You can do the same thing for BA. I will not do it one more time I will not repeat the same thing over and over again. I'll just write you the result. 2EI over L, theta A plus 2 theta B minus 3 phi plus fixed end moment BA. And we call these equations as the slope deflection equations. And we can use these equations when we want to relate the end moments with the end deformations of a member without having to solve the differential equations over and over again. The only thing that we didn't work on is this fixed end moments, and the equations or the magnitudes of the fixed end moments of course depends on the applied loading. If you have a uniform distributed load, we will get different equations for it. A point load, different equations for it. But it doesn't matter if the member is loaded with either point load or the distributed load. This part of the equation is always the same. So we can just examine this equation in two parts. This is the effect of nodal deformations, which we name this part as only nodal deformations case. And this part of the equation is fixed moments, effect of applied loading, without any nodal deformation. So our next task is to figure out what these fixed moments are. Okay, now let's work on the fixed moments. So we will be working on case 1 now. Let's remember what that is. We say that I'm fixing the ends of the member and I have the member loading. So I will be doing the derivation for a uniformly distributed load, W. That's the length of the member. And this is the no nodal deformations. Only member loads. And we said that because of that, for this specific case, I had a fixed moment AB here, and I had a fixed moment BA here. Let's also show the shear forces AY and BY, and of course this point is A and that point is B. So I'll use the same approach. Now let's write the equation for the moment. So I'm taking a section cut. That distance is that's X. So I have a moment here, and on this side I have fixed moment AB, and I have the distributed shear force or the support reaction AY, and the magnitude of the distributed force is W. So if you write the equilibrium equation with respect to that point, we obtain moment as equal to minus fixed moment AB plus AY times X minus W X squared over 2. So that's the equation for moment. Now let's do the write the differential equation. So d square y over dx squared is equal to 1 over EI fixed moment minus AB plus AY times X minus WX squared over 2. And of course, for this case, let's write the boundary conditions. At X is equal to 0, Y is equal to 0, dy over dx is equal to 0, and at X is equal to L, again, Y is equal to 0, dy over dx is equal to 0. Okay, these are the boundary conditions. Integrate that equation once. I have dy over dx is equal to 1 over EI minus fixed moment AB times X plus ay x squared over 2 minus w x cubed over 6 plus c1. Okay, and y is equal to 1 over ei minus fixed moment ab x squared divided by 2 plus ay x cubed divided by 6 minus w x to the power 4 divided by 12 plus c1x plus c2. Okay, so we have these two boundary conditions, so let's use them. At x is equal to 0, y is equal to 0, this tells me that c2 is equal to 0, and again at the same location rotation is 0, this tells me that c1 is equal to 0. Okay, now I want to get rid of ay also, so let's use the other two boundary conditions. So at x is equal to L, I got dy over dx equal to 0, so this tells me that 0 is equal to minus fixed moment AB times length plus AY L squared divided by 2 minus W L cubed divided by 6. And from that equation I obtain AY as equal to 2 times fixed moment AB divided by L minus W L over 3. Okay, that's the expression for AY. Now at x is equal to L, this time y is equal to 0. From that equation I obtain the following: minus MAB, fixed moment AB, fixed moment AB times L squared divided by 2 plus AY times L cubed divided by 6 minus W L to the power 4 divided by 12. Is equal to 0. I think I have to make a correction. Right, this should be 24. So this should be 24. Sorry for that. Okay. Now we should be okay. So let's call this one equation 1. This one as equation star. So inserting 1 into equation star, and I have the following: minus fixed moment AB times L squared divided by 2 plus 2 times fixed moment AB times L squared divided by 6 plus, no, it should be minus W L to the power 4 divided by 18 minus W L to the power 4 divided by 24 is equal to 0. And when you solve that or simplify it, we obtain our fixed moment AB as equal to W L squared divided by 12. So what we learn from here is when I have a fixed beam under uniform distributed load, this is W and this is the length. The moment at this end is in the counterclockwise direction and the magnitude is W times L squared over 12. On the other side, if you repeat that procedure, you find that I have a clockwise moment and fixed moment VA, and the magnitude of that clockwise moment is the same, WL squared over 12. So that's the solution of the case when we have a uniformly distributed load and no nodal deformation. So if I have a member, okay, let's draw that member. Let's say that I have this member, okay, under uniform distributed loading, and I got MAB here and MBA here, and the deformed shape of that member is defined as follows. YA, YB, so this angle, remember that, this angle measured in counterclockwise direction, that's the chord rotation, and the deformation, theta A, theta B, and this is the deformed shape. So a member in this form, loaded with a uniformly distributed load and have the following deformed shape. The end moment MAB is equal to 2EI over L 2 theta A plus theta B minus 3 times chord rotation plus WL squared over 12. And MBA is equal to 2EI over L theta A plus 2 theta B minus 3 phi, and since this moment is in the clockwise direction, this is minus WL squared over 12, and these are the end moment and displacement relationship for a member loaded with uniformly distributed load. And if you think about it, I can have a triangular load here, I can have some point loads here, or maybe partial load, and combination of all the loadings. The only thing that will change in this equation is this fixed end moment part. Okay, so I can do the same derivation for a single point load, for a partial load, for a triangular load, and obtain the expressions for the fixed end moments. And at the end of the day, when we have a different types of loading, I sum up all the fixed end moments from these type of loading, and only this part of this slope deflection equation will be modified. Before going into the analysis of indeterminate structure, I want to do one more derivation, and I obtain another slope deflection equation, and we call these equations as modified slope deflection equations. In that case, this is what I'm going to analyze. Again, we have a member, okay, under certain loading. And this is the local x prime axis, local y prime axis of the member, okay. And here I have a moment, MAB, but at point B, we know that moment is equal to 0. I mean, at point B, we could have a pin support or an internal hinge, and we may have this condition, moment is equal to 0. So I will do the derivation assuming that this moment is equal to 0 now, and see how the slope deflection, or if the slope deflection equation changes, okay? So this shear force is AY, this shear force is BY, and let's plot the deformed shape. So the far end is free to rotate, right? That's the condition of having a 0 moment. Again, the deformed shape, point A can translate, that's YA here. Point B can translate, YB. And that's the chord rotation. That's our phi angle. Now I have a rotation here, theta A, and far end is free to rotate. Okay? And of course, we can have theta B here, but you will see that we will not need it to derive the equation for MAB. So that's why I'm not showing it. Okay? Now let's use the same approach. I'm doing the superposition again. In the first case, no nodal deformations. So I put a hinge support here just to show that moment is equal to 0 and this end is free to rotate. That's the condition of this derivation. So I can have any loading on this one, W, and here this is the fixed moment, AB. I just put a prime here because it's for a specific condition, and plus only nodal deformation case. And here I have MAB. So here no nodal deformation. That is theta A is equal to phi angle, and that's equal to 0. Okay, and we have only member loads in that case. And in the second case, only nodal deformations. That are, you have theta A and phi. I'm not saying that we don't have any rotation here. We do, but I'm not interested here because I'm using the information that moment is equal to 0 or this end is free to rotate. So I'm not interested in the value of theta B. Okay, so again, that's our case 1. That's our case 2. So let's do the same approach, right? So moment, I do take a section cut, that's M, that's AY, that's MAB, and I'm working on case 1 right now, sorry, case 2. And the equation for moment is equal to M minus MAB plus AY times X. But now I use a different boundary condition. I'm saying that at x is equal to L, moment is equal to 0. So this gives me AY as equal to MAB divided by L. And my moment equation is now free of the shear force, and that's equal to minus MAB plus MAB times x over L. Let's continue. Let's write the differential equation. Now d square y divided by dx squared is equal to, let me put primes here, I forgot to put primes. Oops, not here, but here. So let's put all the primes. Alright, now we can continue. Minus MAB prime plus MAB prime times x over L. Integrated one time, dy over dx is equal to minus MAB prime x. I should have EI here, I forgot to write EI, sorry. Okay, x divided by EI plus MAB prime x squared divided by 2 times L times EI plus C1. So at x is equal to 0, dy over dx is equal to theta A. So we say that C1 is equal to theta A. Okay. Again, I'm using the following deformed shape. It tells me that at x is equal to 0, y is equal to ya, and dy over dx is equal to theta A. So these are the boundary conditions. So I use one of the boundary conditions. Let's write down the equation for y. Minus MAB prime x squared over 2EI plus MAB prime x cubed divided by 6L times EI plus theta x plus, I will just directly write YA. Y is equal to YA. So this tells me that C2 is equal to YA. Okay? Again, now let's use the third boundary condition. At x is equal to L, y is equal to YB. So this tells me that YB is equal to minus MAB prime L squared divided by 2EI plus M prime AB L cubed divided by 6L EI plus theta A times L plus YA. And if I simplify that equation, I obtain the following. MAB prime is equal to 3EI over L theta A minus YB minus YA divided by L. And we know that this expression is equal to the chord rotation or the phi angle, and our final equation will have the following form. MAB prime is equal to 3EI over L theta A minus the chord rotation. So our slope deflection equation for this specific case will have the following form. 3EI over L theta A minus phi plus the fixed end moment, calculate for this specific case. And this is the slope deflection or the modified slope deflection equation. So we say the modified equation. Why? Let's go back to our original derivation of the actual slope deflection equations. Now in this derivation we use x is equal to 0, dy over dx. This is the first boundary condition. That's the second boundary condition, fourth boundary condition, and third boundary condition and the fourth boundary condition. And at the end of the day, the slope deflection equation depends on three displacement quantities. Okay. Now in the derivation of the modified equation, I have an additional information here. Moment is equal to 0. So I consider it as my boundary condition, a force boundary condition. So I use it at this point. Okay. This is the first boundary condition that I use. Second boundary condition, third boundary condition, and fourth boundary condition. And at the end of the day, I obtain a moment equation that depends on only two displacement parameters. Why did I do that? Because you will see that it will help us to simplify our solutions, because in order to obtain the moment value at this end of the member, I didn't use the rotation value at the far end. I don't have to calculate it. Okay, so it gives us one unknown less in the solutions. And as a final remark, you can repeat the same procedure, but if you have a uniformly distributed load, this is L, this is W, and we have the fixed moment AB. If you repeat the same procedure for this condition, you will obtain the fixed moment AB as equal to WL square over 8. In this exercise, we derive all the equations that we are going to use in the analysis of indeterminate structures. And the reason of doing all these derivations is to relate the end moments with the end deformations. This is the modified case for the following end forces and for the following deformed shape. We also derive the slope deflection equations for a most general case, and that most general case is with these end force definitions and with the following deformed shapes.